Hello, and welcome to G Fun Facts Online, your go-to source for the most amazing tidbits from the world of science and technology. Today, we're plunging into an incredibly cool topic. Literally. Ever wondered why quantum computers, these futuristic superbrains, need to be colder than the deepest, darkest corners of outer space? We're talking temperatures that make Antarctica feel like a tropical beach? Well, buckle up, because we're about to explore the fascinating world of advanced cryogenic systems and why they're the unsung heroes of the quantum revolution. So what's the big deal with keeping things frigid? It all comes down to something called qubits. Qubits are the fundamental building blocks of quantum computers, and unlike the bits in your classical computer that are just a 0 or a 1, qubits can be a 0, a 1, or both at the same time, thanks to the weird and wonderful rules of quantum mechanics. But here's the catch. Qubits are incredibly delicate. Think of them as tiny, super-sensitive acrobats trying to perform a complex routine. The slightest disturbance, like heat, vibrations, or even stray electromagnetic fields, can make them tumble. This tumble is called decoherence, and it's a quantum computer's worst nightmare. When qubits decohere, they lose their special quantum state, leading to errors in calculations. And that's where cryogenics swoops in to save the day. Cryogenic systems are essentially superpowered refrigerators that create ultra-low temperature environments, often pushing close to absolute zero. That's 0 Kelvin, or minus 273.15 degrees Celsius, or minus 459.67 degrees Fahrenheit for our listeners in the US. Why so cold? Well, these cryogenic systems play several key roles. First, they drastically reduce thermal noise. At these extreme lows, the jiggling and vibrating of atoms pretty much grinds to a halt. This calmness minimizes a major source of interference, allowing those delicate qubits to maintain their quantum states, their coherence, for much longer. Longer coherence means more time to perform complex calculations accurately. Second, these frosty conditions enable superconductivity. Many of the leading types of qubits, like the ones used by giants like Google and IBM, are made from superconducting materials. Superconductivity is this amazing phenomenon where materials can conduct electricity with absolutely zero resistance, but it only happens at cryogenic temperatures. This zero resistance flow is crucial for creating and manipulating qubit states without losing precious energy. And third, the stable, ultra-cold environment helps to isolate and stabilize the qubits. This makes them easier to control and measure with high precision. Better control and longer coherence are the secret ingredients for tackling those mind-bending quantum algorithms. Now you might be thinking, how do scientists even achieve these bone-chilling temperatures? And what's new in this frosty field? The world of cryogenics for quantum computing is advancing at lightning speed. One of the cornerstones is a device called a dilution refrigerator. These aren't your kitchen fridges. They're sophisticated machines capable of reaching millikelvin temperatures. That's thousandths of a degree above absolute zero. For instance, Yulvac recently kitted out Japan's first fully domestic quantum computer with a system that maintains a stable temperature of around 10 millikelvin. That's seriously cool. Then there's Cryo-CMOS technology. Imagine integrating the control electronics, the stuff that tells the qubits what to do, right next to them, in that freezing environment. This reduces delays in complex wiring. Companies like Semiquon are developing these Cryo-CMOS circuits that work efficiently at these extreme temperatures, consuming far less power. Semiquon even unveiled a transistor designed to operate at 1 Kelvin or below. And as quantum computers grow, needing more and more qubits, the cryogenic systems have to scale up too. Think modular. Companies like Bluefors are creating platforms, like their KIDE system, that can support the infrastructure for over 1,000 qubits and allow multiple units to connect. Google's also in on this, patenting a 7-stage cryogenic cooling system designed for multi-unit scaling. It's all about building bigger and better quantum fridges. But that's not all. Scientists are also working on improved materials and insulation to stop any heat from leaking in, better vibration isolation because even tiny shakes can upset qubits, and even alternative cooling methods. We're seeing things like adiabatic demagnetization, refrigeration, or ADR, and even laser cooling for specific qubit types. VTT Technical Research Center of Finland is even exploring an electrical cooling method using something called thermionic devices. Plus, companies like Form Factor are developing high-speed cryogenic testing systems to quickly check these complex quantum chips, speeding up the whole development process. And efforts are underway to make these systems more compact and automated, like Qubit system, aiming to bring cryogenic cooling out of the research lab and into industrial applications. Of course, it's not all smooth ice skating in this cryogenic wonderland. There are some pretty significant challenges to overcome. As you add more qubits, the cooling power needed skyrockets, and managing all the heat from the control wires becomes a massive headache. Keeping the temperature perfectly uniform across a larger system is also tricky. Plus, putting control electronics close to qubits helps performance, but generates more heat inside the cryostat, which is a problem. These systems are also expensive and consume a lot of energy. And imagine the wiring. Connecting thousands or even millions of qubits means a spaghetti junction of wires running into the cold zone, all adding heat and complexity. Even tiny imperfections in the qubit materials, known as two-level systems or TLS, can cause errors, and these can be affected by the cold. And finally, maintenance isn't easy. If something needs fixing, you can't just pop the hood. The whole system has to be warmed up and cooled down again, a process that can take days. So what does the future hold for these quantum iceboxes? Well, the development of advanced cryogenic systems is absolutely vital for the progress of quantum computing. We're likely to see a big push for greater efficiency and compactness, making these systems smaller, cheaper, and less power-hungry. We'll need systems with much higher cooling power to handle the heat from future computers with millions of qubits. Tighter integration between the cryogenics, the quantum hardware, and the control systems will also be key. And of course, the hunt for new materials and cooling techniques will continue. There are even efforts like the Arctic project in Europe aiming to create a standardized supply chain for cryogenic technologies. In conclusion, sophisticated cryogenic cooling isn't just a nice-to-have, it's a core enabling technology for unlocking the incredible potential of quantum processors. By creating that stable, ultra-cold haven for delicate qubits, protecting them from the chaos of thermal noise, these advanced cryogenic systems are truly paving the way for more powerful, reliable, and scalable quantum computers. The constant innovation in this super cool field is absolutely critical to overcoming the current challenges and unleashing the transformative power of quantum computation. And that's a truly cool fact. Thanks for tuning in to Fun Facts Online. Join us next time for more amazing insights from the world around us.